head is attached to a sealed chamber called a plenum. The only time you'll ever see it working is when it finishes. Here's what goes on out of sight. As the teeth scour the rock, the debris falls into the plenum. From the plenum, debris flows out via a giant corkscrew called an Archimedes screw. The debris moves along conveyor belts to the end of the tunnel. The entire machine is as long as a football field. Inching the TBM forward are 29 hydraulic rams.
As the cutter head is going round, cutting the ground, these rams act on the last ring built, shove the whole thing forward, including all this backup equipment, until there's enough space here to build another ring, which is 1.5 meters wide.
Each ring is formed of 10 precast segments brought by train from the head of the tunnel.
Then this red piece here comes into play, and this is called the segment erector.
Even concrete segments have to be handled gently. Chipping opens channels for water. The segment erector uses vacuum suction.
It picks up the individual segments for the ring, places them in position, and the miners bolt them together. And once the ring is complete, the rams can then move against the last ring built and start the cycle all over again.
Every minute, the machine normally moves forward about the length of a finger, 100 millimeters.
100 millimeters a minute doesn't sound a lot, but when these machines are working 24/7, on a good day, they can build over 50 meters of tunnel.
Like other tunnellers on the route, they run into a familiar hazard: chalk.
We knew that it had deep fissures in it, and we knew that those fissures would be containing water.
40 meters below the Thames, the pressure on the cutter head is 4 times the pressure on the surface. If water breaches the cutter head, it could flood the TBM and drown the crew.
On a previous tunnel project, I've been in the tunnel when the lining was breached. I can only compare it probably to a submarine being depth charged.
To counteract the pressure, the plenum behind the cutter head is equally pressurized. It's called an earth pressure balance system.
And what happens with the earth pressure balancing is that if there was a sudden inflow of water during the tunnel operation, the pressurization in the plenum would respond and balance out the pressure.
Thanks to the pressurized plenum, crews bore ahead without a single breach. After 15 months, the TBMs emerge from beneath the Thames. By foreseeing trouble and heading it off, they've jumped ahead of schedule. But more tunnelling lies ahead, as daunting as the Thames, beneath the streets of London. Digging a railway under a metropolis gives architecture the jitters.
When you excavate a hole in the ground, it's almost inevitable that you'll get settlement at the surface. The solution we adopted to try and reduce the number of buildings we went under was to put it wherever possible under an existing busy live railway. That brought its own issues because any mishaps in the tunnelling under the railway could have been disastrous.
And we had agreed with the underground that we would only tunnel as long as the movements were within very, very strict and limited dimensions.
The TBM's earth pressure balancing system is designed to keep the ground over the tunnel from settling. Even settlement, the thickness of a toenail, could cost a fortune.
Indeed, at Highbury Station, we had a settlement limit of 1 millimetre. If we'd have exceeded that, the whole station would close down, cost of £25 million a week.
And that was very anxious moments, because the London Underground could have closed our operation down, could have stopped the project.
6 TBMs in all are burrowing, 2 from the East End and 2 pairs from Stratford. Other crews dig ventilation shafts to dissipate pressure when trains race through the tunnel. The shafts can also be used in an emergency.
To allow the emergency services to get to a failed train in a reasonable time frame, the ventilation shafts had to be located at a sensible distance apart, and that distance was seen to be 3 kilometres.
Crews are working miles apart, yet all the tunnels and shafts must align within millimetres.
Very, very small tolerances, because the actual train, being high speed, can't deviate in line or level. Some very accurate surveying needs to happen on the tunnel rail link. It's so long that you have to take account of the Earth's surface in the surveying.
Such precise surveying couldn't happen without lasers and GPS. Long before trains start to run, the ventilation shafts play a crucial role when the TBMs hit flint.
It's a very hard and very abrasive material. It's been known to completely destroy cutter heads within as little as 200 metres of driving a tunnel.
And so therefore we had to design the head of the tunnel boring machine to be able to crunch through flints and to turn them into smaller parts that we could then take through our slurry machine.
They modify the cutter head with nearly 50 cutter discs, each a ton of hardened steel. They exert so much pressure they shatter flint. Yet even steel discs wear out.
When a tunnel boring machine arrived at a ventilation shaft position, the cutting blades were inspected and, where necessary, replaced. And as a consequence, the tunnel boring machines were capable of completing the whole tunnel from one end to the other without major breakdowns or refurbishments.
I think probably the only major urban tunnelling scheme in UK in my lifetime that's come in on time and budget.
An enormous success story.
In the heart of London, another success story emerges from a big hole. A maintenance depot for Eurostar trains called the Stratford Box. It lies along the London tunnels between the Thames on the east and St Pancras on the west. The ground is so waterlogged it could flood the depot. Engineers have 2 choices.
We could either make the thickness of the base slab very, very, very thick so it stayed in the ground, or you could do what we decided to do, which was to pump.
Underground pumps drain enough water every day to overflow an Olympic swimming pool.
Interesting enough, the water is of such a quality that we have then used that and we give that to the Water Authority for London.
When complete, Stratford Box is 55 metres wide and more than 1 kilometre long.
And such a large box gave us the opportunity to actually say, well, we think we should have a station in this location. The introduction of this station, little did we realise, would actually be the genesis of the Olympics coming to London.
A stone's throw from Stratford Box is a floodplain with 100 empty acres. Using dirt from the box and the London tunnels, engineers raised the land 7 metres above the plain. A perfect site for an Olympic park. London has already put in its bid for the 2012 Games to the International Olympic Committee, the IOC. To win the bid, London has to prove it can move millions of fans speedily and easily, and High Speed 1 holds the answer. shuttles could whiz fans from St Pancras and Ebbsfleet to the Olympic Park at Stratford along the new high-speed 1 route in a matter of minutes.
We were very fortunate in timing that the IOC were coming to London 2 or 3 weeks just before we were about to lay track in the tunnel between Stratford and here at St Pancras.
Holden takes the committee members from Stratford to St Pancras in a fleet of Land Rovers, through the same tunnel where high-speed shuttles will run.
I think that probably helped considerably for London to be awarded the Olympics, to show what a quick connection there was from this part of London to St Pancras.
After the Games, the Olympic site will house a new school, more than 3,000 homes, and one of the largest urban parks in Europe. And that's just for starters.
High Speed 1 is much more than a railway and about getting people from A to B.
It's about bringing dead neighbourhoods back to life.
To begin with, regeneration wasn't viewed as being particularly important, but in my opinion, it's the most important aspect of this railway.
Around here, particularly to the east and to the north of here, was about 67 acres of disused railway land that hadn't been used by the public forever. The whole area was very downbeat and very depressed, and the local people were fed up with it. They wanted change.
In all, almost 200 acres of blight will disappear.
Stratford City and King's Cross Central are the two biggest active development sites in London, and they're both enabled by High Speed 1. They wouldn't be happening if it wasn't for the railway.
As the tracks creep towards St Pancras, a new engineer climbs aboard. Dave Poynton spent half his career working on the Channel Tunnel. Midway through 2005, Rob Holden calls him out of retirement.
Thinking there might be a few days of interesting work, it was something of a surprise when he said, "No, we'd like you to take over and finish the railway." And how could I possibly refuse the opportunity to be there when the last spike went in the rail of a project linking London and Paris I'd started almost 20 years before. There was still a lot of work to do.
Setting ties, laying track, running power lines. They move gas pipes serving half of London without once interrupting service. Near St Pancras, they sink foundation piles within 2 meters of subway tracks, a feat no one had ever done.
And we managed to convince London Underground to let us get on with that work whilst they still had trains running through their tubes.
But along their own tracks, they hit a snag.
Through the trees behind me is the historic parish church of St Pancras. And in the Victorian times, associated with that church was a large burial ground, extending right as far as pretty much where we are standing now. And what the Victorians had to do to build the original station was